So, if you don't mind taking a seat, we'll get started. So for our first talk of the afternoon session, we're happy to have Ting Lu, who's going to talk about the Haar state of OSLQ3 on a monomial basis.
All right, thank you for the kind introduction. So before I start, I would like to say several words on this project. So when I was doing my PhD, I got interested in finding a quantum analog of that famous Weingarten functions on Lie group. But then I find that our knowledge of this quantum Haar state is not as abundant as the classical one. So I decided to first look at these simple examples. And a quick introduction of my research target. So the quantum group OSLQN in my talk will be a hoop algebra rather than a C-star algebra. So everything here is just algebraic. And this is their generators. And this is the commutation rules for those generators. Here, the Q is the quantum determinant. It's just the Q analog of the classic determinant for matrix. And then we have the co-algebra structure on OSLQN. Here is the co-multiplication, and here is the co-unit. By the way, the co-multiplication is a algebra homomorphism. And as a hoop algebra, there is also an antipode. So here, the antipode is defined by the quantum cofactor of an element. So quantum cofactor is just a analog of the classical cofactor. It's just you replace that -1 in the formula by -q. And if q is a real number, then we can define a unique hoop star algebra structure. And the star operation is defined by the antipode. And in this case, we'll call this hoop star algebra as the compact real form, OSUQN. So here, this word compact has no real meaning. It's just an analog of the classical case where the special unitary group is the compact real form of the special linear group. So there's essentially no topology here. And for the Haar state on OSLQN, it is the unique translation invariant linear functional that maps 1 to 1. And we know the existence and uniqueness of this map since a long time. And this is a pure algebraic result because OSLQN is a co-semi-simple hoop algebra. So there is a Peterville decomposition. And to define a Haar state, you just set 1 to 1, and you set the Haar state of all other matrix coefficients to 0. So now it looks like if I want to compute the Haar state of something, I just decompose that into a linear combination of matrix coefficients. However, if you think about it, to find the explicit expression for this matrix coefficient is not easy. OSLQ2, by the work of Masuda, Mimachi, and Nakagami, they find that the matrix coefficient is a Q analog of the little Jacobian polynomial. However, that's the further we can get. If n is larger or equal to 3, then we do not know the explicit expression. So decomposing that into matrix coefficients will not work in general. And here is some existing works on Haar state on OSLQN, or more general quantized algebra of functions. So by the work of Reshetkin and Yakimov, they show that the Haar state on the compact real form of a quantized algebra of function can be written in this form, where this integral is taken on the maximum torus of k. So by their work, we can find how the quantized Haar state changed to the usual integral with respect to the Haar-Mischer as q goes to 1. But if you really want to do computation with their formulation, then there is some problem because the integrand is going to be the trace of an operator on a infinite dimensional space. So this integrand is actually a summation of an infinite series in general. So it's not very easy to compute with this formulation. And in my work, I try to find linear relations between the Haar state of monomials directly coming from the translation invariant condition. So first thing we want to do is to find some necessary condition for a monomial to have non-zero Haar state. And to introduce the result, we have to introduce some concept first. So first, I will say a counting matrix of a monomial is going to be a n by n matrix with non-negative integers, where the aij entry is the number of appearance of generator xij in X. And I will say a matrix is an n by n k integer doubly stochastic matrix if that matrix has non-negative integer entries and the sum of each row and each column equals to k. So this is just an analog of the doubly stochastic matrix in random matrix theory, where the sum of each row and column equals to 1. And here is the characterization of a monomial to have non-zero Haar state. So if the monomial has non-zero Haar state, then its counting matrix, theta x, is going to be a n by n k doubly stochastic matrix for some k. And so this is our characterization. Then the next work we want to do is to find some essential monomials that span all monomials satisfying this condition. And in this slide, I'm going to make some notations first. So ANK is the set of all n by nk doubly stochastic matrices. And I will say a monomial is of order k if its counting matrix belongs to ANK. Then we can show if for each matrix in ANK we fix some special monomial of order k, then all the other monomial of order k can be written as their linear combination. And I'll call the special monomials we pick as a pseudo basis of order k. And you will see why they are just pseudo bases in the next slides. That is, so if I union two of such sets together, they are no longer linear independent because we have the linear dependency induced by this identification. So if I pick a monomial of order k minus 1, I multiply that by dq. Essentially, I'm multiplying by 1. However, if you expand this expression, it's going to be a linear combination of monomials of order k. So it's in the span of pseudo basis of order k. And later on, I will pick a basis from this choice on OSLQ3. Although pseudo bases, they are not really bases, but they arise naturally when we want to evaluate the translation operation, like what we had in theorem 3. So if I take the translation operation of a monomial of order k, then it's going to be a linear combination of monomials of order k, and the coefficients, they are the Haar state of some other monomials of order k as well. So combined with our previous theorem, we can decompose those ys and zs as a linear combination of our pseudo basis of order k. And that's why I want to introduce this pseudo basis. So this equation actually provides the methods to construct linear relations between the Haar state of pseudo basis. So if I take the translation of a pseudo basis of order k, it's going to be a linear combination in this form. And since we identified dq as 1, I raise dq to the power k, it's still 1. But every summand in this thing will be also a monomial of order k. So we can decompose this expression as a linear combination of our pseudo basis as well. Then you plug in the two relation into this translation invariance identity, and you compare the coefficient of Sj, we will find that their coefficients must be the same, and we will get a linear relation between the Haar states of pseudo-bases. And I will call this the derived linear relation as the linear relation derived from equation basis SL and comparing basis Sj. So actually, your equation basis and comparing basis, they can be two different set of bases, but in my research, I just put them as the same basis. So you know how to construct linear relations. Then I also need some important thing called modular automorphism to make our computation easier. So the modular automorphism, it was originally defined on the compact real form. It's defined this way, and it satisfies this crucial property, crucial in my research. And usually when we talk about modular automorphism, we require Q to be real. However, if you release that requirement, if Q is some complex number, it will still satisfy this crucial condition, although it may not be qualified to call them as modular automorphism anymore. But to keep consistent, I will just keep saying their modular automorphism on OSLQN. And other than the modular automorphism, I'll also introduce two important value-preserving homomorphism. The first one is called diagonal flip. You just flip these indices, and you can show it satisfies exactly the same property as the antipode, so it preserves the Haar state value. Similarly, there's you can define the double flip anti-homomorphism. I call it double flip because it's just like you flip the generator matrix along the diagonal, then along the reverse diagonal. And you can show it's still it's acts quite like the antipode, so it preserves the Haar state as well. Then let's focus on OSLQ3. So this is going to be the generator matrix, to just save some space. And the pseudo basis of order m I pick is going to be in this form. And each pseudo basis of order m will be indexed by 5 numbers. First is the order, and that is the index of generator A, index of generator R, index of generator G, and index of generator T. And for simplicity, I'll just write the index of generator E as n, and I will denote their Haar state in this form, in short. And by using the two value preserving homomorphism I just introduced, we can show that if you switch the index R and L, or you switch the index S and T, the Haar state value stays the same. And then this is the monomial basis I picked from the pseudo basis of order m's. So essentially, they are monomials without generator A, or monomials without generator K, or monomials without generator E. And it's easy to say they're linear independent, and to say they actually span every monomial of order m, you just realize if you have generator A, K in your pseudo basis, you somehow move them together and replace that pieces by this by the right-hand side of the equation. So they are the bases, and here's the mean theorem. It's just the Haar state of those bases. So first is the Haar state of this essential monomial, and then the Haar state of the monomial basis will be expressed as a multiple of this essential monomial. And down here in the denominator, this is just the Q analog of the combinatoric numbers. So you can check from their expression that indeed you switch index R or L or index S or T, the expression stays the same. And I'll briefly talk about how I compute them. So start from the first result. So to compute our first result, we have to construct something I call source matrix. It's constructed by using the linear relation derived from equation basis C to the M, E to the M, G to the M, and using the comparing basis listed here. So we have 5 comparing bases, give us 5 linear relations, and you will realize the 5 linear relations, they only include this following unknowns, the Haar state of these 6 monomials. They're the only unknowns appearing in these 5 linear relations. So I have 5 linear relations, 6 unknowns. I need 1 more. And the 6th linear relation is derived from this one. So by these 6 linear relations, I can construct a linear system involving monomials that contain this piece in their expressions. And I will call such a linear system as a source matrix of order M. And the only non-zero right-hand side will be the Haar state of this monomial. So this is going to be a recursive system. You will first solve the Haar state of this monomial from the source matrix of order M-1, and then use that as the right-hand side. And by the way, the right-hand side for first-order source matrix is just 1 equals to 1. And then for information, this is the solution to the source matrix, and the last line is our first result. And then to compute the Haar state of my monomial basis, we have to use the modular automorphism to construct some extra linear relations. So by using the modular automorphism, I can somehow teleport this generator on the very left to the very, on the very right to the very left, but still keeps the Haar state the same. But this algebra is non-commutative, so the decomposition of first line and the third line is going to be different. If you compare the difference, you will be able to construct some extra linear relations between the Haar state of monomials of order M. And as I stated here, you can actually use this recursive relation. So yeah, this is actually a recursive relation on the number of generator E. So on the right-hand side, all the monomials, they have n-1 generator E, and on the left-hand side, it's a monomial with n generator E. So you can use this recursive relation to compute actually all the Haar state of all pseudo bases of order M. And this is going to serve as your one of the boundary points corresponding to R equals to 1. Yeah, I still have a few minutes. So let me finally make a comment on computing the Haar state on more general space. So it is still possible to construct the source matrix for any n. But the problem is in larger n, there will be n factorial many linear conditions in my source matrix. And for now, I do not have a very efficient method to compute those linear relations. I can just do them one by hand. So it's doable for n equals to 3. There's only 6 relations. It's doable for n equals to 4. I can write a computer program. But in general, this as n increase, the number, they go exponentially. So I will still need some more efficient method to construct those linear relations. And also, we do not, in general, know how to enumerate pseudo bases of order M on larger groups. And thank you. That's the end of the talk.
So we have time for 1 or 2 questions.
Yeah. Help to explain n.
To see the structure.
To see the structure, yeah. So I will definitely look into some special functions. So this is just the first step of my research. Yeah, if you have better suggestions, then maybe we can talk later. Yeah.
Any others? If not, let's thank our speaker.